So good morning, good afternoon, good evening. Welcome to this instance of the Antrea community meeting. Today is Tuesday, July the 20th, or if you are in the US, it will be still Monday, July the 19th for you. And for today, we have only one topic on the agenda. And we should have Hong Liang, and sorry if I get your pronunciation of your name wrong, presenting about the AntreaProxy design with TC, and this design should include support for both NodePort and services of type load balancer. No other topic was booked for today's meeting, so I believe that we can start with this presentation about the AntreaProxy design. So Hong Liang, please go ahead.
Okay, thanks, Salvatore. Wait a minute, I'll share the screen.
Are you okay? Yes, we can see the screen now.
Okay. Hello, guys. This is a presentation about the new design of AntreaProxy to support the NodePort load balancer and cluster IP on Kubernetes node. And so far, it's Linux only now, but I think some parts of this design can be also applied to Windows in the future. Okay, the outline, motivation, and current design and the new design, the support cases of the new design. First, the motivation. The target of this design is to remove the AntreaProxy. If the AntreaProxy is removed, then a lot of CPU circuits and memories can be saved. We don't need to handle a lot of IP table entries. Instead, we may account lots of OS flows. In current design, the service can be only supported fully when the client is from a pod. If the client is from remote host, AntreaProxy has to need the help of AntreaProxy to redirect the service traffic into Antrea gateway. In addition, to get the better performance, if the client is from hosts, remote hosts, the performance of AntreaProxy is limited by AntreaProxy now. Okay, this is the current design. We can see that when the client is from a pod, all services can be supported without the AntreaProxy. This kind of service, this kind of traffic can be handled inside the OS. However, when the client is from remote or a Kubernetes node, the service traffic must pass through AntreaProxy to do DNAT. That's the root cause of the AntreaProxy performance is limited by AntreaProxy. Here is a new design. Okay, I'll introduce the new design in two parts. The first part is Linux only, I think, is how to redirect remote and local host service traffic to Antrea gateway directly without passing through AntreaProxy, and how to make the response traffic back to the client. And the new design uses Linux TC to handle the NodePort and the load balance traffic from remote clients. And for NodePort traffic from local host, Linux TC is used. For load balance traffic from local host, the new design uses unlinked route to handle it. The first part resolves the issue of bypassing AntreaProxy. Without AntreaProxy, AntreaProxy must handle the complete life cycle of service traffic. I think this part can be, the second part. The second part is OS pipeline. I think this part can be used in Linux as well as Windows. There are three main issues. First, how to do SNAT for source traffic. The second one, how to handle the destination MAC address of the response traffic. Then the third one, compatible with the legacy design. Okay, this will be talked later. I'll introduce the new design, the first part. Take NodePort for example. Okay. For request NodePort traffic from remote client, first a filter will created and attached to the here take ETH0 as an example. Will attach to ETH0's ingress for every NodePort service. Here we take 30,001. That's the destination port. By default, the filter will be put on train 0. The handle ID is generated by a generator according to NodePort IP address, layer 4 protocol, and the NodePort port number. These 4 factors can ensure that handle ID is unique. When deleting the NodePort service, the handle ID is used to index the filter and delete the filter. Then what the filter do is that it will be redirected to entry gateways egress. Okay, we can see the TC command here. And pay attention that if the interface has more than one IP addresses, the above command will be generated for every IP address. And we can also say that the ETH1, this command will be also generated for ETH1 as ETH0. Okay, the next one. For request NodePort traffic from local host client, there are some differences. First, the clients from local host, and then the target NodePort IP addresses can be loopback IP 127.0.0.1 or ETH0's IP address and ETH1's IP address. Filters should be created and attached to loopback's egress, not ingress like ETH0. And the source MAC of the packets should be modified to entry gateway's MAC address. Otherwise, the packets will be dropped by OVS. Okay, here is the TC command. Okay, next one. Okay, for response, the request job is that here is the response. Like IP tables, TC field, Linux TC supports hierarchical chains. We know that the only difference of NodePort is the port number. To redirect the response traffic to interface where this request traffic is from, according to the source IP of the traffic. Some basic filters will be created to redirect the master traffic to a target subchain. Note that if the source IP address and the destination IP address are the same, it indicates that its request traffic is from loopback. The filter should have higher priority. Otherwise, it will be masked by other filters to ETH0 or ETH1. That's not what we want. Okay. Next for subchain is where the second layer filters locates. When NodePort is created, the filter will be created and attached to the subchain. The filter matches the packets according to the source port, and the action is to redirect the match response traffic to the interface where it's requested traffic from. If the subchain is for loopback, the source MAC and the destination MAC address should be also rewritten to L0. Otherwise, the loopback will drop the packets whose source or destination MAC address is not L0. Okay, here is the TC command. Okay, next one for load balancer. Here, we assume that the load balancer traffic can be only from, assume that the load balancer can be only from remote, can only pass through the default route. That's ECS0. If there are multiple default routes, select the entry with the lowest metric. And that means the highest priority. And we don't consider about the complicated routing configs. Okay, that's almost the same with NodePort TC filters. The difference is the IP address is the load balancer external IP and its port. Okay, next for load balance traffic from localhost. Here, unlinked route is used for routing the load balancer request traffic into entry gateway. The target IP address is the load balancer external IP. The output interface is entry gateway, and the next hop is the service virtual IP address. OAS table 20 will handle the ARP request of the service virtual IP address. Okay, next for response traffic. For response traffic, it has two directions. One for entry gateway. This traffic is request is from Kubernetes node, and the one for default route interface is request traffic is from a remote client. And then we should add a higher priority filter to match the traffic whose request traffic from entry gateway. And then we can bypass the traffic back to entry gateway. And the left traffic is for default route interface. Okay, next one. Next for cluster IP. For cluster IP, this client can be from pod or Kubernetes node. Here is for Kubernetes node. When cluster IP is created, and if there is no cluster IP so far, okay, then the unlinked route will be created for the cluster IP, and the prefix is 32. That's the longest mask for root. Okay, then like this one, add a new cluster IP, then a new unlinked route will be generated and replace the old one, and the destination block will expand. Okay, its prefix is 29 now. When add a new one, a new cluster IP, it can the current root item can cover this IP address. Do nothing. For the next one, the current root item can cover this cluster IP. So it continue expand. Finally, the service CIDR will be and there is always only one root entry for routing cluster IP. Okay, the next part is the new OS pipeline. The red ones are new added. The yellow ones are modified, and the blue ones are not changed. I also take an example to explain the new OS pipeline. Here is the case. Okay. So to be simple, I'll omit some tables. Table 24 is the new table for transforming SNAT of service traffic, and this drawing is also a new drawing for SNAT. For the first packet of request, this table can do nothing, just plus new plus track. Okay, the next we can see that this is the new action. This new action, this is for the first packet of server traffic from remote host client. Let's see what this table does. Okay, we can see the state. The state here. What it does is it will match the service traffic its first packet and generate a flow to table 70 file. This learned flow match the response packet of the NodePort. The learned flow will rewrite the destination MAC with the current packet's source MAC address. Also set reg 1. This means that the packet should be output through gateway. Okay, this, and then also set reg 016 to 1. This means the packet should be output. Another action is this action is important. This means that this packet requires SNAT. If the external traffic policy is local, this one to be set. Okay, that's the other ways. After DNAT at table 42, the destination IP address is 10.10.0.4, and the destination MAC address is rewritten at table 70. Okay, then go to table 100 file. This flow is a new added one, and it's used to match the service packets from gateway. Otherwise, the service packets will be matched by this one. That's not what we want. Table. This is the new table. At here, this the new table, but this ID is not the new one. It's for table hairpin S9 table before. Now the hairpin S9 table ID is 108. According to the city states and the Reg 416, the action is city and commit to S9 join. Here, the S9 IP address is gateway's IP address. Then after the S9, the packet is output. Okay, for the second packet, the response packet. When passing table 24, it will be transformed. Its destination IP will be recovered. And when passing 30, when passing table 30, it will be transformed again. Its source IP will be recovered. And when passing table 31, according to its city state, the packet will be sent to table 15 and then to table 70. When the packet arrives table 70, according to its destination IP address, and its destination MAC address will be rewritten. Its output interface will be decided at the table 18. That's the older way, but because their destination IP address is recovered to the client, so now these flow entries will hit the packet. This entry is flow. This flow entry is for it. This state is replied tracked and its service traffic. It will be the master package will be sent to 70 file. The 70 file is a new table. This table is, I have mentioned this table before, at table 30 file. The generated learn flow is located at the table 70 file. The first packet of a remote client will trigger a flow at the table 70. And this flow is used to set destination MAC address, output interface, and output register. Okay, this as the second packet is not from gateway, so the first flow will not match it, and the last flow match it. Okay, then the second packet will return to the client. Next is the third packet, the order routine. So note that the packet 2 can be transformed at table 24, but packet 3 cannot, because there is no connection track on S9 drawn about the current connection. And it can be only transformed at table 30. In general, so there will be some different for packet 2, packet 3 from packet 2. Okay. Next, nothing different. As the packet 3 is from gateway, it will hit the first flow of table 100 file. At this table, the fourth flow will hit the packet. As the current connection has been committed, the first packet has been committed for current connection. So it won't be the current packet will be transformed without committing again, and each source IP will be gateway's IP address after after the CT operation, and it will be output. Okay, next for another case, its endpoint is on host network. That's the first difference is at table 70, and we can see that as its destination IP address is on another Kubernetes host Kubernetes nodes, and it won't hit any flow here. So it can only hit this flow, and this flow is prepared for it. It's set the destination MAC address as entry gateway's MAC address. Also set the SNAT register. As it's hairpin traffic because it's from entry gateway, and it will be out of OAS pass through entry gateway. So it must be SNATed. Okay, the next for hairpin traffic, the SNAT can't, the IP address of SNAT can't be entry gateway because the entry gateway will drop the packet if its destination is entry gateway. So its source address should be a different one. Here we use a service virtual IP address to do SNAT. Okay, here is the supported cases of the new design. This case, the NodePort or load balancer, his external traffic policy is local, and its endpoint is on host network. That means it needs the packet needs to reserve its source IP address, and its destination is on hostnet. Then the response traffic, the response packet won't be routed into OAS, and this and the connection will be broken. The NodePort load balancer almost the same, and cluster IP is all supported. Okay, that's all. Any questions?
Thanks a lot for this presentation. It was extremely informative. So if the community has any question, curiosity, observation, please go ahead.
Okay, about part 1 or part 2?
Is there any plan to cover the use cases that we don't support today? I'm referring to the table you showed at the very end. Those cases where the external traffic policy is local and the destination endpoint is in the host network. Do we have any plan to address it somehow?
Yes, but I have investigated some possible, but I don't. I think it's not so worth it to do it. I can use Linux TC filter to do some to add a mark to TC, add a mark, but that will introduce another join to TC filters. Current design for TC filters is stateless, and that if the TC filters introduce stateful, I think that will make effect to the performance.
But only I try to ask you in the issue. Could we use connection tracker only for the case that the backend server is a host network port?
That will introduce the CT for TC filters.
Sure, but what's the issue with that? If it's only for the case of the host network port.
If we introduce the CT operation for TC filters, that will take effect to all traffic. We only for this case. If we only for this case.
Why is that? Could we match IP first? Let me see. Could you match the IP first?
If you access to a service IP address, you don't know whether its endpoint is on a port CIDR or a hostnet. You don't know that, so you can't do that at first.
Why we don't know? We know what the host IP.
Oh, okay. I know what you mean, but okay, I know what you mean.
I don't know. I'm not sure if other people here has any opinion, but I feel it's hard to say this. These are not important case, right? I mean, I'm not very sure, but I assume maybe there are some use cases for example, external traffic policy equals local, and then the backend is a host network port.
In my opinion, I think it's minority one.
But how you know? I'm not certain either, but I'm just wondering if it's supported, and if I really have some service in host network.
We can also support it, but we will change some behavior. We can do SNAT for it, and then we can. I don't know
I
if
saw about
it's
that too.
correct.
I saw about that too. I think that at least it's better than not supported. But yeah, as you said, then you change the behavior of external traffic policy local. So.
Okay, got it.
How about let's do some evaluation on these two options, SNAT or connection tracker. If SNAT is much simpler, yeah, maybe we can also consider it. but I'm not sure it's much simple or not. Why not you symbolize to potential approaches, and then we can decide which way to go.
Oh, sorry. Okay.
No, I just mean, well, why not let's look at 2 options and see if we can choose one way to go.
No, sorry. I just didn't catch what you said. Or could you please point a slide or case number to show the question?
Okay, probably I can summarize my thoughts offline with you.
Maybe there's a solution for this case. I think maybe if we use the packet mark, and the connection mark to mark the traffic from the gateway interface, and we do some special handling in the output chain, maybe we could avoid maybe we could just redirect the reply traffic with specific connection mark back to the gateway interface.
Oh, I have tried this idea. You said you add a mark to the request packet, but the response packet.
That's why we need the connection mark. The connection mark is for the session, not for packets. So if you set the mark to the connection, then the reply traffic will also has that mark, so we can match on that mark. But
this mark can be.
It will be a little complicated. It's a little similar to the envoy redirection case. We can discuss this offline.
Okay, and this mark can be set as join 0, not the join that cell with the host join, host network join.
Sorry.
Does this mark can be set at OS pipeline?
Yes, OS pipeline can set the packet mark. Then we need to match the packet mark and set the connection mark in IP tables.
Okay.
Yeah.
I see. That's. I think this is possible. I see. I think this can be possible. Maybe I need. I'll try this idea later.
Okay.
Do we have any other question regarding the proposed design here?
I do have a quick question if Hongliang doesn't mind. I'm looking at the row number 17 and 18 here. I was not noticing that if the client part is from the remote node, and depending on the external traffic policy, we may or may not need SNET in 2 different cases. I might missed when you presented, but could you explain a little bit on why that is the case?
If I list all cases, the time will be out. All the cases, and I just list some the typical cases.
Yeah, right. I'm just talking about this specific case because, for example, if we have a pod from a remote node trying to access a NodePort service. Now, why is that? Because of the external traffic policy, we don't need SNET for a local case.
you with sorry, I didn't catch what you say. What
I think Yang's question is about why, in the case external traffic policy is local, you do not need SNAT. Is that correct, Yang?
Yeah.
Yeah, I think it's part of the Kubernetes specification, but I'll let Hong Liang reply.
That's the how to say that the Kubernetes
it's the specification, I believe, Hong Liang, that requires when traffic is local, it requires the traffic to come to the server with the client IP, right? To not be snatted.
Yes. Thanks.
Oh, okay, I see.
Any other question? We still have quite some time. Okay, I have two very simple questions, mostly as usual because of my ignorance. So considering these few use cases that at the moment we are not supporting, is this affecting in any way conformance tests? I mean, is there any conformance test that explicitly verifies if NodePort traffic works with external traffic policy local in all cases? Or is conformance tests are still passing fine?
I may not catch what you said, but is that you mean if I have added any test to current cases about NodePort or load balancer?
No, sorry, I meant something different. I mean, if now we replace kubeproxy, we completely replace it with AntreaProxy, will the conformance test, like the CNCF conformance test that we already execute in our CI, will they still pass, or will there be any conformance test that might start not passing because of these use cases that we are not supporting at the moment? Or
I have added some E2E test for these cases, but conference test I didn't do anything about it.
Yeah, I mean, we don't have maybe we don't have to do anything about it.
I suggest let's just run all the conference tests and see which cases are failing, and let's investigate. And if the conference test won't fit our design now, and maybe we can add some new E2E tests to cover and skip those.
Sounds good. Thanks, Jiacheng. And the other question that I had was whether this design, as it is, works for IPv6 out of the box, or whether we will need some tweaks for making sure that that everything works fine with IPv6 as well.
Oh, okay. I have considered about IPv6, but the time is limited, and I have this. I didn't talk about it. I have spotted at the beginning of this design. I have considered about IPv6, and I have tested about these cases at IPv6. But there are some issues. But it depends on Kubernetes upstream. So I didn't. For example, for how to list the Kubernetes node network CIDRs. There are some issues about the dual stack for Kubernetes service. So the current design is limited by these issues.
I see. Okay, thanks. Thanks for thanks for bringing this up. That's good to know. And at least from what you've seen, are those issues that are already being tracked by the Kubernetes community, or is it something that maybe if we want to have them addressed, we should fix them by ourselves? I mean, my question was more about so these issues that you have identified are issues that are already known to the Kubernetes community, and maybe there's someone being addressing them or not.
Yeah. Hongliang, are you still online?
Oh, sorry. Oh. Hello, Salvatore. Is that question for me?
Yes. I mean, you mentioned that there were some for IPv6. You found some upstream issues that were preventing you for implementing design for defining a solution for IPv6. I was just curious if those issues were already tracked in the Kubernetes community, or whether there was no one looking at those issues at the moment.
I have this issue. I have noticed that there are issues tracking this. There is a issue tracking this one, but it seems that it hasn't been resolved. I have noticed this about a few weeks ago. So I think I need to find it later. I didn't remember the specific problem now, but I just remember that. So sorry.
No problem. I mean, I mean, you answered my question that it was an issue that was already known to the community and not just something that you find it for the first time. So thanks for your answer, and that is all from me in terms of questions. Is there any other comment about the design observed today? A design that we discussed today. Sorry, I don't know why I used observed. I'll wait 20 more seconds in case there is any other question. Perfect. Apparently there aren't any more questions, so I would like to thank Hongliang for this very informative presentation. And the only follow-up question is, what are the next steps for the implementation of this design?
The next one is how to remove AntreaProxy totally. The current design is that we use the endpoint of Kube API server to fetch the service or other information from Kube API server. This is not perfect because we fetch the information from only API server. If the API server is more than one, it needs we don't know is class IP address. So the next step, I think I need to resolve the issue of how to handle the load balancer of Kube API server.
All right. Thanks. Thanks for this answer. Okay, and perhaps that is really all for today, at least for this topic. Anything else that the community would like to discuss for today's meeting?
Okay, I think it's all now.
Well, I'll wait a few more seconds to check if there is any other topic that you would like to bring up. And it appears that it's really all for today. So I would like to thank again Hongliang for this presentation. Thank again everyone for attending this meeting. And well, the only thing left to do is to say, wish everyone a good afternoon, a good evening, or a good day. And we'll talk again. We'll meet again in 2 weeks' time. Thanks everyone for joining, and have a good one.
Thanks.
Thank you.
Bye.
Thank you.
Thanks.
Bye.